November 24th, 1944, 27,000 feet above Tokyo. Captain Yasuo Kuwahara pushed his Kawasaki Ki 61 fighter through air so thin his engine screamed in protest. The altimeter needle climbed past 26,000 feet. 27,000, 28,000. His vision narrowed at the edges. The cockpit temperature read -40 degrees. Ice crystals formed on the inside of his canopy, where his breath condensed and froze instantly. Above him, silver shapes carved contrails across the winter sky, B-29 Superfortresses, 111 of them, flying in formation at 30,000 feet like they owned the air up there, which, Kuwahara realized with a fury that tasted like bile, they did. His Ki 61 reached 29,000 feet, and the engine began to cough. The fighter that had seemed so powerful at 15,000 feet now felt like it was swimming through mud. Every control input came slow. Every maneuver cost altitude he couldn't afford to lose. The Americans flew 5,000 feet higher, moving at 350 miles per hour, and Kuwahara's most desperate climb had given him maybe one attacking pass before his fuel ran out and his engine quit entirely. He squeezed the trigger anyway. 20mm cannon shells arced toward the nearest bomber. Most fell away harmlessly. A few struck the fuselage, and Kuwahara watched them punch holes that should have been fatal. The B-29 kept flying, kept its position in formation, didn't even waver. Then the bomber's defensive guns opened up. Remote-controlled turrets tracked his fighter with mechanical precision. 50 caliber rounds tore past his canopy. One struck his wing root. Another shattered his windscreen. Kuwahara dove away, engine temperature redlining, fuel gauge dancing near empty, knowing he'd accomplished exactly nothing except confirming what every Japanese fighter pilot already understood. The Americans had built something impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 3 years earlier, Boeing's engineering offices in Seattle hummed with the kind of desperate energy that comes from knowing you're building something that shouldn't be possible. The specifications sat on Wellwood Beale's desk, like a dare. Range, 5,300 miles. Service ceiling, over 30,000 feet. Bomb load, 10 tons. Pressurized cabin, remote-controlled defensive armament. Every requirement pushed beyond what existing technology could reliably deliver. The men who gathered around the Model 345 blueprints understood they were attempting something fundamentally different from every other bomber in the sky. The B-17 flew at 25,000 feet maximum. Crews wore oxygen masks, electrically heated suits that worked when the wiring didn't short out, and still got frostbite on missions lasting 8 hours. The accepted wisdom said you couldn't fly higher because human beings couldn't survive up there, and you couldn't pressurize a bomber because the first piece of flak would turn the reinforced fuselage into a death trap. Boeing's solution ignored conventional wisdom entirely. The Model 345 would fly at altitudes where German and Japanese fighters couldn't reach, where anti-aircraft guns couldn't accurately target, where the air was so thin that a bomber moving at 350 miles per hour would be untouchable. All it required was solving about 3,000 engineering problems simultaneously. The pressurized fuselage added 3,000 pounds of weight. That meant less bombs or less fuel. The remote-controlled gun turrets required electrical systems more complex than anything ever installed in a combat aircraft. The 4 Wright R3350 engines needed to produce 2,200 horsepower each at 30,000 feet, where the air pressure was 1/3 of sea level, and the entire aircraft had to be manufactured at a scale and speed that would deliver hundreds of bombers before the war ended. On September 21st, 1942, Eddie Allen lifted the XB-29 prototype off Boeing Field's runway. The test pilot, whose judgment insurance companies trusted more than their own actuaries, took the silver giant through its paces with methodical precision. Wingspan 141 feet, Empty weight 74,000 pounds fully loaded, 140,000. 4 engines that each weighed more than a Volkswagen, and that revolutionary pressurized cabin that made the entire concept possible. The first flight revealed the bomber's breathtaking potential. Alan climbed to 25,000 feet without crew members needing oxygen masks. The remote gun turrets tracked targets with computerized precision. The aircraft handled like something 20,000 pounds lighter. For 30 minutes, the impossible dream looked like it might actually work. Then engine number 4 started smoking, not the white vapor of condensation, black smoke that meant oil was burning where it shouldn't. Alan shut down the engine, completed the flight, and landed with one engine trailing ribbons of fire. The ground crew extinguished the blaze. Alan climbed out and filed a report that filled 3 pages with technical details. But the conclusion was simple. The Wright R3350 engines had a fatal flaw. The magnesium crankcase meant that when these engines caught fire, and they caught fire often, the magnesium burned at 5,600 degrees Fahrenheit, hot enough to melt through aluminum wing spars in seconds, hot enough that no fire suppression system could stop it. The rear cylinders overheated because cowling clearances were inadequate. Valves failed because fuel distribution was uneven. And when ignition occurred, the magnesium components transformed into incendiary devices that consumed the aircraft from inside. December 30th, 1942. Eddie Allen brought the second B-29 back from a test flight, with engine number 4 trailing fire at 5,000 feet. He landed with the cockpit filling with smoke, the wing spar already damaged, minutes away from structural failure. Fire crews extinguished the blaze. Alan climbed out. The Army awarded him the Air Medal for saving the aircraft. 50 days later, he would climb back into that same bomber for one more test flight. By then, President Roosevelt had already made his promise to Chinese leader Chiang Kai-shek at the Cairo conference. B-29s would bomb Japan from Chinese bases by April 1944. When Roosevelt made that commitment, fewer than 100 B-29s existed, and only 15% of them were actually flyable. The Army had ordered hundreds more. Workers in Wichita were assembling bombers outdoors in temperatures 20 degrees below zero, rotating in 20-minute shifts to avoid frostbite. $3 billion. More than the $1.9 billion spent on the Manhattan Project. The most expensive weapons program in American history now rested on engines that killed the airplanes they powered. Boeing's revolutionary idea had created a bomber that could fly higher than any enemy fighter could reach. But first, it had to survive its own propulsion system long enough to prove the concept worked. February 18th, 1943, 12:17 p.m. Boeing Field. B-29 serial number 41003 climbed through 5,000 feet with Eddie Allen at the controls. The test flight was routine, checking fixes implemented after the December fire. Allen had flown burning aircraft before. He had landed bombers that should have killed everyone aboard. His calm under pressure was legendary. The number 1 engine caught fire at 5,200 feet. Allen shut it down immediately, activated the carbon dioxide fire suppression system, turned the bomber back toward Boeing Field. Standard emergency procedure. He had done this before. The fire should have gone out. It didn't. A second fire erupted. Radio operator Harry Ralston's voice cut through the cockpit intercom, stripped of the professional calm that aircrew maintained even in crisis. Allen, better get this thing down in a hurry. The wing spar is burning badly. The B-29 was no longer an airplane with an engine fire. It was a structure being consumed from within by magnesium burning at temperatures that could melt steel. The fire ate through hose clamps, valve housings, mounting brackets, components that held the engine to the wing. Parts began falling away. The bomber shed debris over Seattle neighborhoods as Allen fought to keep it airborne long enough to reach the runway. 3 crewmen jumped at 250 feet. Too low, parachutes needed at least 500 feet to deploy properly. The silk canopies were still deploying when the men hit the ground. None survived. Allen kept flying. The runway was visible. Boeing Field was right there. The B-29 clawed through air thick enough to fly in. The magnesium fire now burning through the main wing spar, the single structural member that kept the wing attached to the fuselage. At this point, there was no saving the aircraft, only the question of where it would hit. It came down short of the runway. The fry packing plant, a meat processing facility, sat directly in the impact zone. The bomber crashed through the building's roof at 12:28 p. Eddie Allen died instantly. 8 other crewmen died in the impact. 19 workers in the packing plant, processing meat for wartime rations, were killed when 5,600-degree fire swept through the building. A firefighter died fighting the magnesium blaze that consumed what remained. Total, dead, 32. The backlash was immediate. $3 billion. 32, dead. The most expensive weapons program in American history had just incinerated itself over Seattle. Critics in Congress called for cancellation. Army Air Forces officers questioned whether the entire concept was flawed. The engines were obviously the problem. Everyone could see that. Wright Aeronautical's R3350 was killing the airplanes it powered, but there was no alternative engine capable of producing 2,200 horsepower at 30,000 feet. No time to develop a replacement. No way to meet Roosevelt's deadline with a redesign. The Army gave Boeing an ultimatum that bordered on impossible. Fix the engines. Keep the pressurized cabin that added 3,000 pounds and drove the entire design philosophy. Meet the April 1944 deadline for combat operations, or watch the entire program transfer to Consolidated's B-32, a conventional, unpressurized bomber that abandoned the altitude advantage Boeing had bet everything on. Spring and summer of 1943 became a race between engineering and politics. Boeing engineers, Wright Aeronautical technicians, and Army Air Forces specialists converged on the R3350 problem with wartime urgency that made peacetime development schedules irrelevant. The engine went through tens of thousands of design modifications, not hundreds, tens of thousands. Every component that failed got redesigned. Every system that contributed to overheating got re-engineered. The cowling, the metal shroud around the engine, was completely redesigned to increase airflow over the rear cylinders. The original design choked cooling air at low speeds, exactly when overloaded bombers needed it most during takeoff. The new cowling opened up passages that doubled airflow when the aircraft was climbing at full power. The carburetor system was scrapped entirely. Early R33. 5 Cero engines mixed fuel and air in carburetors, then forced the mixture through a poorly designed elbow into the supercharger. The sharp bend created turbulence that distributed fuel unevenly across 18 cylinders. Some cylinders ran lean and overheated. Others ran rich and fouled spark plugs. Direct fuel injection eliminated the carburetor and the elbow, spraying precisely metered fuel directly into each cylinder. Hot spots disappeared. Power output became predictable. Propeller cuffs, metal fairings around the base of each propeller blade, were added to divert cooling air directly onto exhaust valves. The valves were failing because they operated at temperatures that exceeded their metallurgical limits. More airflow meant lower temperatures. Lower temperatures meant valves that didn't disintegrate after 50 hours of operation. Later production runs would replace the magnesium crank cases with steel. Heavier, but steel didn't burn at 5,600 degrees. The early B-29s, already in production, kept their magnesium hearts. Those aircraft would fly combat missions, knowing that any engine fire could become unsurvivable within seconds. Even with all the modifications, the R3350 remained temperamental. Time between overhauls increased from 100 hours to 400 hours by war's end, barely adequate for an engine that needed to power 15-hour combat missions. The engines would kill B-29 crews throughout the war, but they would kill fewer, and enough would survive long enough to prove whether Boeing's impossible bomber actually worked. By May 1944, 130 B-29s, completed the 11,500-mile journey to bases in China and India. Workers had built them faster than the fixes could be implemented. Some aircraft carried engines with all modifications. Some carried engines with half. All carried crews who understood they were flying experimental bombers into combat before testing was complete. June 15, 1944. The first B-29 mission against Japan since Doolittle's raid in 1942. 68 bombers took off targeting the Imperial Iron and Steel Works at Yawata. 47 reached the target. 6 aircraft were lost. The mission failed to destroy the steel works. Bomb accuracy from altitude was worse than predicted. Weather was worse than predicted. Everything was harder than the planning document suggested. The critics sharpened their arguments. $3 billion. Inadequate results. Crews still dying. But buried in the after-action reports was a data point that changed everything. Japanese fighters attacked 184 times during the mission. 0 B-29s were shot down by enemy aircraft. The altitude advantage worked exactly as designed. Japanese fighters couldn't reach 30,000 feet with enough energy left to fight. When they tried, they arrived gasping. For air, unable to maneuver, unable to maintain pursuit speed. The bombers' defensive systems had done their job, but the real defense was altitude. Thin air as armor. The concept Boeing had bet $3 billion on was proving correct in the most demanding laboratory imaginably. Combat against a determined enemy fighting for survival. Summer and fall of 1944 revealed a pattern that vindicated Boeing's vision and exposed the R-3350's continuing treachery. B-29s kept dying on the ground, overloaded with fuel and bombs on tropical airfields where temperatures climbed above 100 degrees. The right engines overheated within minutes of throttle up. The aircraft needed every foot of runway to stagger into the air at maximum gross weight, 140,000 pounds. When an engine caught fire during that critical climb, pilots had seconds to decide, abort and probably survive, losing the mission. Or continue and possibly die, completing the takeoff. The early B-29 tactics combined maximum weights with high-temperature airfields, creating conditions that defeated even the modified cowlings and fuel injection systems. The engines swallowed their own valves. Exhaust valves that failed from heat stress dropped into cylinders and destroyed pistons. When magnesium components ignited during takeoff, the resulting fires reached temperatures approaching white heat. 5,600 degrees Fahrenheit, intense enough that main wing spars burned through in seconds, giving crews no time to evacuate before structural failure. Mechanics developed rituals. Some whispered prayers over engine cowlings before closing them. Others performed checks in specific sequences that had no technical justification but felt necessary. Crews watched other bombers burn on takeoff and knew their turn was coming. The engines would kill randomly. No pattern predicted which aircraft would make it and which would become funeral, Pyrrhus at the end of the runway. But the bombers that survived takeoff and reached operational altitude became something the Japanese had never encountered. Untouchable. 8,000 miles across the Pacific, Japanese military planners stared at intelligence reports that defied everything they understood about industrial warfare. The numbers were impossible. Boeing's Wichita facility, 1 B-29 every 6 hours. Seattle plant, 160 bombers per month by mid-1945. Total American heavy bomber production, more aircraft in 4 months than Japan produced in an entire year. The mathematics were obscene. One American factory employed more workers than some Japanese cities contained. American industrial capacity exceeded Japan's by ratios that made strategic planning meaningless. And now, those factories were producing bombers that Japanese fighters couldn't touch. Lieutenant General Torashiro Kawabe, Deputy Chief of the Imperial Japanese Army General, Staff. Read the assessment with the kind of cold clarity that comes from understanding you've already lost. The report was clinical, precise, devastating. American B-29 specifications. Service ceiling 31,850 feet. Maximum speed 357 miles per hour at 25,000 feet. Range 5,630 miles. Defensive armament 12 50 caliber machine guns in remote-controlled turrets. Bomb load 20,000 pounds maximum. Japanese interceptor capabilities. The Ki-44, Japan's best high-altitude fighter, topped out at 30,000 feet in ideal conditions. At that altitude, the pilot had no energy left for combat maneuvering, no speed for pursuit, just enough power to watch silver contrails pass overhead while his engine screamed at maximum output and his controls felt like moving through concrete. The Ki-44 could barely touch 30,000 feet. The B-29 cruised there comfortably. Crews working in pressurized cabins equivalent to 8,000 feet elevation. No oxygen masks. No electrically heated suits. No frostbite. Just men in shirt sleeves drinking coffee, while Japanese fighters struggled and died 5,000 feet below. The report included testimony from fighter pilots who'd attempted intercepts over Jawata. Captain Toshio Sakagawa described climbing through 28,000 feet in his Ki-44, pushing the fighter to its absolute limit, watching the B-29 formation sail past 3,000 feet above him. He'd fired anyway, 20mm shells that fell away before reaching the bombers. Then, his engine temperature spiked, his fuel gauge hit reserve, and he'd spiraled down through 20,000 feet of empty sky knowing he'd accomplished nothing. Major Teruhiko Kobayashi, commander of the 244th Sentai, assigned to defend Tokyo, provided tactical analysis that read like a coroner's report. To intercept B-29 formations at operational altitude requires positioning fighters at 30,000 feet before the enemy arrives. Climbing to intercept altitude after radar detection provides insufficient time. The Ki-61 can reach 28,000 feet with experienced pilots. At that altitude, the fighter has perhaps 90 seconds of combat capability before fuel exhaustion or engine failure. Attacking from below is suicidal. The bomber's defensive fire is overwhelming. Attacking from above requires altitude advantage we cannot achieve. Head-on attacks offer the only viable tactic, but closing speeds exceed 600 miles per hour. Pilots have one firing pass. If that fails, the fighter cannot catch the formation again. Kobayashi's assessment concluded with brutal honesty. We can damage individual bombers. We cannot prevent the raids. American altitude advantage makes traditional fighter defense ineffective. The technical specifications revealed why. Japanese fighter engines were optimized for performance at 15,000 to 20,000 feet, the altitude range where Pacific War combat had historically occurred. The Mitsubishi Kinsei, the Nakajima Ha-109, even the excellent Mitsubishi Ha-112, all produced maximum power at medium altitudes. At 30,000 feet, they gasped. The Ki-84 Hayate, introduced in 1944 as Japan's answer to American fighters, could reach 30,000 feet in perfect conditions, but perfect conditions meant light fuel load, no ammunition, no external tanks, and an experienced pilot flying a freshly maintained engine. In combat configuration, carrying enough fuel for 30 minutes of operations, the Ki-84 topped out around 27,000 feet. And at that altitude, the fighter had no energy reserves for combat. Turbochargers could have solved the problem. American fighters used turbo superchargers that maintained sea-level engine, performance at high altitudes. But Japanese industry had never mastered turbo supercharger production. The technology required specialized metallurgy, precision manufacturing tolerances, and industrial capacity Japan didn't possess. Attempts to reverse engineer captured American equipment revealed the gap between what Japanese engineers could design and what Japanese factories could build. The altitude crisis extended beyond fighter performance. Anti-aircraft guns defending Japanese cities were calibrated for bombers operating at 20,000 to 25,000 feet. The Type 88 75mm gun could barely reach 30,000 feet with maximum elevation. At that range, shells lost velocity. Fuses became unreliable. Accuracy degraded to the point where gunners were firing at coordinates rather than visible targets. Fire control systems designed for medium altitude. Bombers couldn't track targets at 30,000 feet, moving at 350 miles per hour. The mathematics of ballistics broke down. Shell flight times exceeded 20 seconds. In that interval, a B-29 formation could maneuver 3,000 feet laterally, rendering predicted impact points meaningless. Japanese radar systems compounded the defensive problem. Early warning networks could detect incoming raids, but tracking accuracy at extreme altitude was poor. Fire control radar that worked adequately against medium bombers lost precision against targets at 30,000 feet. Fighter direction became guesswork. Interceptors scrambled toward estimated positions, burning fuel climbing to altitudes where the enemy might or might not be. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The operational consequences became apparent during the November 24, 1944 raid on Tokyo. 111 B-29s attacked the Dail Rifas, Nakajima Aircraft Engine Factory at Musashino. Japanese air defenses threw everything available into the defense. The 10th Air Division scrambled 125 fighters, Ki 44s from the 47th Sentai, Ki 61s from the 244th Sentai, Ki 84s from the 73rd Chutai, even obsolete Ki 43s that had no business attempting high-altitude intercepts. Every available aircraft, every pilot, every ounce of remaining fuel dedicated to stopping the American formation. The fighters made 184 attack runs. They fired thousands of rounds. They attempted every tactic Japanese fighter doctrine recognized: head-on passes, diving attacks, formation disruption attempts, ramming attacks by pilots willing to die if it meant taking one bomber with them. 0 B-29s were shot down by enemy aircraft. The defensive guns below fired 1,256 rounds of 75 mm ammunition, shells that cost hours of precision manufacturing labor, shells that required propellants Japan could barely produce, shells that exploded at the wrong altitude, the wrong time, the wrong place. Because fire control systems designed for 20,000 feet couldn't accurately target 30,000. 0 B-29s were shot down by anti-aircraft fire. One bomber was lost to a ramming attack when Lieutenant Kazuo Tamuda drove his Ki 44 directly into a B-29's tail section at the cost of his own life. The sacrifice destroyed one aircraft out of 111. The mathematics were brutal. To stop a 100-bomber raid using ramming tactics required 100 pilots willing to die. Japan didn't have 100 experienced pilots to spare. Not anymore. The formation bombed through solid cloud cover, bombardiers releasing weapons at coordinates on maps rather than visible targets. Accuracy was poor. Less than 25% of bombs hit within 1,000 feet of aim points. The Nakajima factory sustained minor damage. Production barely slowed. But the raid proved something that terrified Japanese military planners more than the bombing itself. American bombers could operate over Tokyo with near impunity. The most heavily defended target in Japan, the city with the highest concentration of fighters and anti-aircraft guns, and Japanese defenses had accomplished almost nothing. The battle reports from November 24th landed on Lieutenant General Kawabe's desk 3 days later. He read them with the kind of attention men give to autopsy results. The clinical details of failure: ammunition expenditure, massive. Aircraft sorties, maximum effort. Results, negligibly. Kawabe had spent 30 years in military service. He understood operational realities. He'd commanded divisions in Manchuria. He'd planned campaigns across Asia. He knew what achievable military objectives looked like. And he understood that stopping high-altitude B-29 raids with Japan's current defensive capabilities wasn't achievable. The mathematical reality was inescapable. American bombers could fly missions whenever weather permitted. Japanese fighters consumed fuel and pilot hours, attempting intercepts that rarely succeeded. The exchange ratio favored the enemy by margins that made sustained defense impossible. For every B-29 destroyed, Japan lost multiple fighters, expended thousands of rounds of irreplaceable ammunition, and burned fuel reserves that couldn't be replaced. The strategic assessment Kawabe, drafted for Imperial General Headquarters, abandoned the optimistic language that typically characterized military reports. Current defensive measures against high-altitude B-29 operations are insufficient. Enemy bombers operate beyond the effective ceiling of available interceptors. Anti-aircraft artillery cannot reliably engage targets at operational altitude. Radar systems provide inadequate tracking data for effective fighter direction. Modifications to existing fighters to improve high-altitude performance would require 6 to 9 months of development and retooling of production lines. Availability of specialized materials necessary for turbo-supercharger development is severely limited. Industrial capacity for implementing design changes across fighter production is inadequate. Recommendation: accept that B-29 raids cannot be prevented with current resources. Focus defensive efforts on minimizing damage through passive measures. Disperse industrial production. Develop decoy targets. Expand firefighting capabilities in urban centers. The recommendation was an admission of defeat without using the word. Kawabe understood how it would be received. Military culture demanded that every challenge could be overcome through sufficient determination and sacrifice. Suggesting that a problem had no military solution contradicted everything the Imperial Japanese Army represented. But the mathematics didn't care about military culture. American industrial capacity had produced a bomber that flew where Japanese fighters couldn't reach, and nothing in Japan's strategic arsenal could change that fundamental equation. The Boeing B-29 represented something unprecedented in military aviation. Not just a better bomber, not just superior engineering, but a weapon that operated in an entirely different performance envelope from anything an enemy could field against it. The pressurized cabin that Boeing engineers had spent 3 years perfecting wasn't a luxury feature or an experimental novelty. It was the key that unlocked an altitude advantage Japanese forces couldn't counter. At 30,000 feet, the mathematics of aerial combat inverted. Traditional fighter tactics assumed interceptors could climb to bomber altitude with enough energy left for combat maneuvering. The B-29's operational ceiling broke that assumption completely. Japanese fighters could reach 30,000 feet, barely, with no reserves for fighting. Captain Yasuo Kuwahara, who'd attempted intercepts during the first Tokyo raids, described the experience in testimony recorded weeks later. The Ki 61 climbs well to 25,000 feet. From there to 30,000 is a struggle. The engine loses power. Controls become sluggish. Above 28,000, I'm managing the aircraft at maximum performance with zero margin for error. When I reach 29,000 feet, I can see the B-29 formations clearly. Silver aircraft in perfect formation, contrails stretching across the sky. They look close enough to touch, but they're flying at 31,000 or 32,000 feet. That 3,000-foot difference is insurmountable. I can fire at them. 20mm shells that arc upward and fall away before reaching altitude. I can maneuver aggressively, trying to gain another 1,000 feet, but every aggressive turn bleeds energy and drops me back down. The bombers fly straight and level, maintaining formation, while I'm barely keeping my fighter airborne. The few times I've gotten close enough for effective attacks, their defensive fire is overwhelming. Remote-controlled turrets track fighters with precision no human gunner could match. 50 caliber rounds coming from multiple directions simultaneously. One bomber can concentrate fire from 4 turrets on a single fighter. The closing speeds are so high that I get one firing pass, maybe 2 seconds to aim and shoot, then I'm past the formation, or out of fuel, or my engine's overheating. Flying against B-29s at altitude isn't combat. It's watching an enemy operate where you can't reach them, knowing they can see you struggling below, powerless to stop them. The testimony wasn't isolated. Fighter pilots across Japan's air defense network reported identical experiences. The altitude ceiling wasn't just a performance specification. It was an operational barrier that separated two entirely different kinds of warfare. Below 30,000 feet, Japanese fighters could fight. Above it, they could only watch. American bomber crews experienced the inverse reality. Inside pressurized B-29 cabins, the war looked different from how crews in B-17s and B-24s experienced it over Europe. Sergeant Robert Morgan, veteran of 25 missions over Germany in Memphis Belle, transferred to B-29 operations and described the transformation in letters home. Flying a B-17 at 25,000 feet meant you lived in your oxygen mask. You wore electrically heated suits that worked maybe half the time. Your hands went numb after an hour. Your face froze. You couldn't eat during 10-hour missions because taking off your oxygen mask long enough to chew food would leave you hypoxic and confused. In the B-29 at 30,000 feet, we work in shirt sleeves. The cabin pressure equals 8,000 feet. We can take off oxygen masks and walk around. Some guys eat sandwiches. Others read books during the long flights to Japan. The bombardier can spend hours tracking targets without his judgment degraded by oxygen deprivation. German fighters over Europe came at us from every angle. We lost entire formations to Me-109s and FW-190s that could climb to our altitude and fight. Japanese fighters show up below us, struggling to climb higher, and by the time they reach our altitude, they're too exhausted to fight effectively. It feels like cheating, like we're playing a different game than the enemy. The psychological dimension of altitude advantage extended beyond crew comfort. B-29 crews maintained peak cognitive function throughout 15-hour missions because their bodies weren't fighting thin air. Decision-making stayed sharp. Coordination remained precise. Fire control operators could track multiple fighters simultaneously because they weren't managing oxygen deprivation symptoms. Japanese pilots fighting at maximum altitude dealt with hypoxia as an additional enemy. At 30,000 feet, even with oxygen systems, human performance degraded. Reaction times slowed. Vision narrowed. Complex decisions became difficult. Pilots attempting aggressive maneuvers at that altitude risked blackouts from G-forces acting on bodies already starved for oxygen. The operational advantage compounded. American crews stayed sharp during missions that lasted half a day. Japanese interceptor pilots burned through their physical reserves in 30-minute flights that pushed human and machine to absolute limits. The exchange ratio favored bombers not just because of technical superiority, but because American crews could maintain performance levels their opponents couldn't match. By January 1945, the pattern was undeniable. B-29s flying at design altitude owned Japanese airspace. Fighters scrambled, anti-aircraft guns fired, radar tracked formations from horizon to horizon, and the bombers cruised overhead, dropping ordnance, taking reconnaissance photographs, mining harbors, whatever the mission required. While Japanese defenses spent resources, they couldn't afford trying to stop raids they couldn't prevent. The industrial mathematics behind this asymmetry revealed the full scope of American advantage. Boeing's Seattle facility employed 27,000 workers across multiple shifts. The Wichita plant added 7,500 more. Bell Aircraft in Marietta, Georgia brought another 30,000 employees to B-29 production. Total American workforce dedicated to building superfortresses exceeded 60,000 skilled workers. Japan's entire aircraft industry employed fewer people than Boeing's Seattle plant alone. The production numbers reflected this disparity with brutal clarity. American factories delivered 200 B-29s monthly by mid-1945. Japan's total bomber production for all models combined peaked at 150 aircraft monthly in 1944. Before American raids destroyed the factories producing them, Each B-29 represented 160,000 man-hours of labor. American industry was producing the equivalent of 32 million man-hours of bomber construction monthly. Japan couldn't match that output if every factory in the country stopped building anything else and focused exclusively on bombers, which was impossible because those factories were already building fighters, training aircraft, and replacement parts for equipment being destroyed faster than it could be replaced. The supply chains supporting B-29 operations revealed advantages that extended far beyond aircraft production. Each bomber required 35 miles of electrical wiring. American factories produced that wiring in unlimited quantities. Japanese manufacturers struggled with copper shortages that forced substitution of inferior materials. Each aircraft carried 3,000 instruments. American precision manufacturing delivered those instruments with tolerances measured in thousandths of an inch. Japanese industrial capacity couldn't maintain those tolerances under wartime conditions. Quality control degraded as experienced workers were conscripted for military service. Each bomber consumed 55,000 individual parts during construction. American logistics networks delivered those parts on schedules that enabled continuous production. Japanese supply chains broke down under Allied submarine warfare that interdicted raw materials from Southeast Asia. The fuel equation magnified every other disparity. B-29 operations from the Marianas required aviation gasoline in quantities that staggered imagination. A single mission to Tokyo and back consumed 14,000 gallons per bomber. Burned 1.4 million gallons of fuel. American refineries produced 4 million barrels of aviation gasoline monthly, 38 gallons per barrel, 152 million gallons total. Enough to fuel continuous operations, while maintaining massive training programs that graduated more B-29 crews weekly than Japan-trained pilots monthly. Japan's aviation fuel production peaked at 70,000 barrels monthly in 1944, 2.6 million gallons. The Americans burned more aviation fuel in 1 week of operations than Japan produced in a month. And Japanese production was declining as American submarines sank tankers bringing crude oil from the East Indies. The strategic impossibility became visible in logistics that Japanese planners couldn't solve. To mount effective defense against B-29 raids required keeping fighters fueled, armored, and maintained at readiness levels that consumed resources faster than they could be replaced. Each interceptor sortie burned fuel that couldn't be spared. Each engagement expended ammunition that couldn't be manufactured quickly enough. Each damaged fighter required replacement parts that didn't exist. American losses were replaceable. Completely. Rapidly. A B-29 shot down over Tokyo was tragic for the crew but strategically irrelevant. 2 more bombers rolled off production lines before the wreckage cooled. Japanese losses were irreplaceable. Each fighter destroyed represented manufacturing capacity diverted from other critical needs. Each pilot killed represented years of training investment that couldn't be recovered. Major General Curtis LeMay arrived in January 1945 to command the 21st Bomber Command with a reputation for ruthless efficiency and willingness to ignore conventional wisdom. He studied 3 months of mission reports with an engineer's cold analysis and reached a conclusion that shocked everyone who understood what the B-29 was designed to do. High-altitude precision bombing wasn't working. The bombers owned the sky above 30,000 feet. Fighters couldn't touch them. Anti-aircraft fire was ineffective. The defensive advantage was absolute, and they weren't destroying targets. Cloud cover over Japan was constant. Industrial targets disappeared under weather fronts that lasted weeks. Bombardiers releasing bombs from 6 miles up through solid overcast were aiming at coordinates on maps, not factories they could see. Accuracy was abysmal. The Norden bomb sight, the classified technology that supposedly could drop ordnance into a barrel from altitude, was useless when clouds blocked targets from view until seconds before release. The jet stream made everything worse. Winds at 30,000 feet over Japan exceeded 300 miles per hour. Bomber formations flying into headwinds crawled across the ground at walking speed. Flying with the jet stream, they rocketed over targets so fast that bombardiers couldn't track aim points. The wind threw bombs miles off course. Missions that should have destroyed factories left them untouched, while ordnance cratered empty rice paddies. LeMay's solution violated every principle the B-29 was built on. Strip out most defensive guns to save weight. Load up with incendiary bombs instead of high explosives. Fly at 5,000 to 8,000 feet at night. Attack when Japanese defenses couldn't see formations coming until they were overhead. The irony was brutal. The airplane designed to fly higher than any enemy fighter could reach would win the war by flying lower than even obsolete interceptors. The pressurized cabin, the revolutionary technology that made 30,000-foot operations possible, would become irrelevant. Crews would fly unpressurized at altitudes where they didn't need it, breathing naturally in air thick enough to sustain them. March 9th to 10th, 1945, Operation Meeting House. 334 B-29s hit Tokyo at low altitude, carrying incendiary clusters designed to create firestorms in Japanese cities built largely from wood and paper. The bombers flew through searchlight beams that turned night into day, through anti-aircraft fire that killed 14 aircraft, through ramming attacks by pilots willing to die if it meant taking one bomber with them. Approximately 100,000 people died in one night. More than either atomic bomb would kill. The firestorm consumed 16 square miles of Tokyo. Japanese defenses optimized for high-altitude intercepts couldn't handle the tactical shift. Searchlight batteries designed to illuminate bombers at 25,000 feet couldn't track aircraft weaving through the city at 5,000. Anti-aircraft gun set for high-altitude fuses fired shells that exploded thousands of feet above the attacking formations. The low-altitude missions proved something unexpected. The engines, the R-3350 power plants that killed crews during high-altitude takeoffs, finally had enough cooling air. At 5,000 feet, the atmosphere was dense. Airflow over cowlings was massive. The rear cylinders that overheated at altitude stayed cool. The valves that failed from heat stress survived. The magnesium components that ignited at thin air operating temperatures remained below combustion points. The engines that were villains at 30,000 feet became reliable at 5,000. But the missions also validated Boeing's original concept in ways LeMay's tactical revolution couldn't erase. When B-29s needed to fly high, when the mission demanded altitude instead of surprise, Japanese fighters still couldn't stop them. August 6th and 9th, 1945, Enola Gay and Boxcar carried atomic bombs to Hiroshima and Nagasaki, flying at 30,000 feet. No Japanese fighter got close. The interceptors that scrambled couldn't reach operational altitude before the B-29s were already over targets. The anti-aircraft guns that fired couldn't touch aircraft at 31,000 feet. The bombers cruised to their release points at altitudes where they were visible but untouchable, dropped weapons that ended the war, and flew home without serious opposition. The accounting revealed both triumph and tragedy. Total B-29s built: 3,970. Total cost: $3 billion, $52 billion in 2024 currency. Combat losses: in the Pacific, 414 from all causes. B-29s lost to engine fires on the ground and in the air. Hundreds. B-29s shot down by Japanese fighters at operational altitude, negligible. The final statistics told a story of asymmetric warfare that no amount of Japanese determination could overcome. B-29 operations from the Marianas flew 33,000 sorties, dropped 147,000 tons of bombs, lost 414 aircraft to all causes. That's a loss rate of 1.25%. For comparison, B-17 operations over Europe sustained loss rates exceeding 5% on some missions. The difference was altitude. German fighters could reach B-17 formations and fight effectively. Japanese fighters could reach B-29 formations and die trying. The 3,000-foot ceiling difference between design altitude and enemy capability created an operational advantage that shaped the entire Pacific Air Campaign. Japanese fighter pilots knew they were fighting a losing battle. Captain Kuwahara, who survived the war, recorded his perspective decades later with the clarity of distance. "We understood the mathematics. American bombers flew where we couldn't reach them. When they chose to fly low, we could engage, but they came at night with numbers we couldn't match. When they flew high, we were spectators watching our cities burn. From altitudes we could see but not attack." The B-29 wasn't just a better bomber. It was a different kind of weapon entirely. Our fighters were optimized for combat at 20,000 feet. Their bombers operated at 32,000. That 12,000-foot difference represented technological and industrial advantages we couldn't overcome. We had brave pilots. We had adequate fighters for their designed missions. We even had some weapons that could damage B-29s when we could reach them. What we didn't have was the industrial capacity to build fighters that could operate effectively at 30,000 feet in sufficient numbers to matter. America built what we couldn't, and that difference decided the war. The pressurized cabin that Boeing engineers had perfected wasn't just a comfort feature. It was the technological foundation that enabled altitude advantage. Without pressurization, B-29 crews would have suffered the same oxygen deprivation, cold, exposure, and physical degradation that limited B-17 operations. With pressurization, they maintained peak performance during missions that lasted 15 hours and covered distances that exceeded 5,000 miles. The 3,000-pound weight penalty that critics said made pressurization impractical was the price of admission to an operational envelope Japanese fighters couldn't contest. Every pound of reinforced fuselage structure, every component of the pressurization system, every piece of equipment that made shirt-sleeve operations possible at 30,000 feet, bought altitude advantage that saved lives and delivered bombs. Wellwood Beale's revolutionary idea, the concept that altitude advantage mattered more than defensive firepower, proved correct in ways that transcended individual missions. The B-29 forced Japanese air defenses to prepare for threats they couldn't effectively counter. Resources spent developing high-altitude interceptors that barely worked. Anti-aircraft guns positioned to fire at 30,000 feet. Tactics optimized for formations that might or might not appear at design altitude. The mere existence of a bomber that could fight at 7 miles up changed how Japan defended itself, even when American commanders chose to attack at lower altitudes. The capability remained present, unused but available, waiting for missions where altitude advantage mattered more than payload or surprise. The engineering legacy extended far beyond World War II. Pressurized combat aircraft became standard for every air force that could afford them. The concept bile, championed in 1940 that crew comfort and performance mattered as much as guns and bombs, shaped every bomber and transport aircraft designed after the war. The B-29's pressurized fuselage wasn't a luxury feature or a failed experiment. It was the template for modern aviation. The human cost of proving Beale's concept was calculated in numbers that revealed both vindication and tragedy. Eddie Allen died with 8 crewmen testing an aircraft that wasn't ready to fly. 32 total dead in that Seattle crash. Hundreds more killed in engine fires during training and combat operations. Every B-29 lost to mechanical failure represented crews who died not from enemy action, but from technology that promised safety at altitude and delivered death on the ground. Yet those same crews, when they survived takeoff and reached operational altitude, experienced warfare their counterparts in other bombers never knew. B-17 and B-24 crews over Europe flew unpressurized missions through flak that killed indiscriminately and fighter attacks that turned formations into debris fields. They wore oxygen masks that froze their faces, electrically heated suits that failed and left men with frostbite, requiring amputation. They made decisions while hypoxic, reactions slowed by oxygen deprivation they couldn't detect until too late. B-29, crews operating at design altitude worked in pressurized comfort, equivalent to 8,000 feet elevation. They drank coffee. They moved through the aircraft without cumbersome oxygen equipment. They stayed sharp through 15-hour missions because their bodies weren't fighting altitude. When Japanese fighters appeared below them, struggling to climb higher, B-29 gunners engaged from a position of complete advantage, rested, alert, operating weapon systems that required mental clarity to use effectively. The strategic impact of those 147,000 tons of bombs exceeded the simple tonnage statistics. B-29 mining operations closed Japanese harbors and destroyed maritime shipping that fed Japan's war economy. Incendiary raids burned 67 Japanese cities and displaced millions of workers from industrial production. Precision strikes against aircraft factories, oil refineries, and steel plants degraded manufacturing, a capacity that Japan couldn't replace. The atomic missions that ended the war were enabled by everything that came before. Enola Gay and Boxcar flew to their targets using navigational techniques developed over hundreds of conventional bombing missions. They operated at altitudes validated by thousands of combat sorties. They relied on maintenance procedures refined through brutal experience with temperamental engines. And they proved that Boeing's impossible bomber could deliver weapons that changed warfare fundamentally. $3 billion, 3,970 aircraft, 33,000 combat sorties, 147,000 tons of ordnance delivered, 414 aircraft lost. 80 B-29s shot down by Japanese fighters across all missions and altitudes combined. 0 B-29s shot down by enemy aircraft when operating at design altitude of 30,000 feet or above. The mathematics were undeniable. Japanese pilots called the B-29 impossible, not because it couldn't be built, but because it operated in an environment their fighters couldn't contest. The altitude ceiling wasn't just a specification. It was an operational barrier that separated American capability from Japanese capacity to resist. Captain Kuwahara, flying his Ki-61 fighter through thin air at 29,000 feet, watching silver contrails stretch across the winter sky 3,000 feet above him, understood the impossible mathematics viscerally. They can see us struggling below. We can see them cruising overhead. The distance between us is only 3,000 feet, but it might as well be 3,000 miles. We lack the engines to bridge that gap. We lack the industrial capacity to build those engines. We lack the fuel to operate fighters at maximum performance constantly. We lack the time to develop solutions. We have only determination, and determination cannot overcome physics. 29 proved that altitude was armor. That thin air was a weapon. That engineering advantage backed by industrial capacity could create operational asymmetry an enemy couldn't overcome through bravery or sacrifice. The pressurized cabin Boeing bet $3 billion on made-possible missions Japanese defenses couldn't prevent. The 3,000-pound weight penalty bought altitude advantage that decided the air war over Japan. Wellwood Beale's revolutionary idea succeeded because it recognized a fundamental truth about aerial warfare. The side that controls the altitude controls the engagement. Boeing built a bomber that flew where enemies couldn't reach, and in doing so, created a weapon that changed the Pacific War's outcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.